now. Okay. Okay. Right. Welcome all to Data Search Research Talk. Today, our speaker is Dr. Fernando. He was one of my peers at University of Oregon, so I invited him over. He finished his PhD recently at University of Oregon, and is now a lecturer at Rice University. Previously, he obtained his MSc in electrical engineering and BSc in computer engineering, both from the Michoacan State University in Mexico. I hope I pronounced it correctly. Yes.
That's totally fine, Sensei, yeah.
All right. And his research interests are in the intersection between cross-lingual learning and information extraction. So you will see, given that we are in Sri Lanka and we are doing a lot of work on Sinhala and Tamil along with English, this cross-lingual work would be quite interesting to us. And you can understand that Louis is coming from that perspective as well, where most of the work is done for English. So this cross-lingual work is our bridge to the greater space of mainstream NLP. So without taking too much time, I shall invite Fernando to start his talk.
Awesome. Thank you, Nisansa. I am very grateful to be here. I hope that this talk will be as interesting to you as it is to me. So as Nisansa said, my research interests are between cross-lingual learning and information extraction. And most of the work that I've done is on the task of event detection, but I'll talk about that in a little bit. So first, I'd like to begin by addressing how in recent times, we have become increasingly reliant on applications that have NLP backbone, right? Things like the multiple versions, the multiple flavors of the personal assistant, Siri, Alexa, Google Assistant, and so on, right? But also things like the auto-completion on our phone, or the translation services of Google Translate, right? And even things as disruptive as ChatGPT has been in the past few months, right? However, and I'm sure you guys know about this, there's a research imbalance in NLP work, right? Where most of the work is done on a small subset of high resource popular languages. And there you can include things like, of course, English, but Chinese, Spanish as well, Hindi, and others, right? But there's a huge set of languages that do not get the spotlight, right? And this makes sense if you think about it, because the more popular languages, the more resources it will have behind it, right? The more speakers it has, the broader the impact the research on this language is going to be. And even if you want to create a new resource, right, like an annotated data set, it will be easier to find speakers and they will be cheaper to hire, right? So it makes sense that most of the work is done on these languages. But that doesn't mean that we shouldn't pay attention to the others, right? So cross-lingual learning aims to address this research imbalance. So it wants to sort of like create a bridge between a high resource source language and a lower resource target language. So the objective of the way it attempts to do it is by transferring the knowledge that you acquire from a high resource language like English or Chinese, and transfer it somehow to a less popular language like Urdu or Swahili, right? And works on this domain usually work under certain assumptions. The more strict of those is the zero-shot setting. So what zero-shot setting means for cross-lingual learning is that you don't have any annotated data for the target language, right? So for instance, if you're working with English and Chinese, just to have a pair of languages, right? So if you're using English as the source language, you only have annotated data in English, and you don't have any annotated data in Chinese, right? So you train your model using the annotated data in English, but then you evaluate your model performance on Chinese, right? So that's the gist of cross-lingual learning. And you usually use popular languages to do these evaluations, but the idea is to create methods that will work for less resourced languages, right? So of course, this cross-lingual setting brings with it additional difficulties, right? That are not present in a monolingual setting where you train on the same language you evaluate, right? So here you have both syntactic differences and also differences that come from the grammar of the source and target language, right? So on the syntactic front, you have things like the word order of the language, right? Some languages are written from left to right, and others are written from right to left. But you can also have things like they have entirely different symbol sets or alphabets, right? So for instance, Chinese, Japanese have different a different set of symbols. Even things like Russian have different set of symbols to English. In Spanish, we have different letters that do not exist in English, and so on and so forth, right? And then from the grammar point of view, you have things like non-existing conjugations, for instance. So for example, in Spanish, we have 18 different tenses, and English only has 12. So that means that some of our verb tenses do not exist in English, or do not have an exact equivalent in English, right? And then you have things like words that do not exist in one language but do exist in the other, or polysemous words, which are words that have multiple meanings. And sometimes each of those multiple meanings are different words in the other language, right? So that creates additional complications. And in order to overcome these difficulties, people working on cross-lingual learning take advantage of cross-lingual resources. So I'd like to talk a little bit about those, just to give you a little bit more of context about our work. So the most expensive, most scarce, but also most useful resource to parallel or cross-lingual resource to have is to have a parallel corpus, right? So when you have text that has been expertly translated from one language to the other. And of course, like I said, this resource is very scarce because it's very expensive to create. And even though there exist some examples of this type of resource, they're usually highly domain specific. So for instance, the religious texts like the Bible or the Quran, they have been expertly translated to multiple languages, but they are very domain specific, and they sometimes use like out of date language, right? So that limits their applicability a lot. Then on the next level, you have pseudo parallel corpus. And in order to get these resources, you usually leverage things like machine translation, so Google Translate, or even things like Wikipedia, where you can assume that the Wikipedia pages for the same concept or same topic in two different languages should have somewhat parallel text, like it should talk about the same stuff, right? Even though it's not perfectly aligned. And then after that, after that you have what we call lexicons or bilingual dictionaries. So these are just collections of pairs of words in the two languages. And these are more common. There exist bilingual dictionaries for many different pairs of languages, right? But the issue is that they're usually incomplete and they are very prone to containing errors. Now, there are also what we call second order cross-lingual resources, and they're called second order or second level because they are obtained from one of these first level resources, so to speak. And one of these is what we call multilingual embedding. So multilingual embeddings are just a multilingual extension of the of the monolingual word embedding. And if you don't know what word embeddings are, they are just vectors of real numbers that are used to represent the words in a language. And the vectors should capture the semantics behind the words by displaying some desired properties. So for instance, in the latent space created by these vectors, the words or the representations for similar words should be close to each other, right? That's the main characteristic that you want to have for this embedding. So for instance, the representation for the word cat and the word kitten should be close to each other because they're basically referring to the same animal, right? And they should be closer to each other than they are to the representation of dog. At the same time, they should be closer to dog than they are to the representation of house, right? Because at least those are animals and house is an object. So by displaying these properties, that you can also do some sort of like math, fun math things with these word embeddings, right? So a classic example is that if you have the representation of the word king, and then you subtract the representation of the word man, and then you add the representation of the word woman, you should arrive somewhere in the vicinity of the representation of the word queen, right? So these word embeddings allow you to do these sort of like math operations with words, which is fun. Now, if you extend this idea to multiple languages, right? Then that means that, for instance, the representation of the word cat and the word gato in Spanish, which is cat, right, should be close to each other in the latent space, right? So that's basically just the multilingual extension of the normal word embedding. Now, the problem with word embeddings and multilingual embeddings for that matter is that once you compute them, they are fixed. So when a word has multiple meanings, right? That single embedding, that single representation needs to capture all of the meanings for that word. And that becomes a problem, right? So for instance, here, in the example down here, you have these two very different sentences, right? So John was fired from his job and the police fired a shot at the suspect. So here you have the word fired in both sentences, but the yes, having switching slides quite frequently.
Yeah, I was wondering what was happening actually.
Yeah.
Can you see it now?
Great. Yes. Yeah.
Okay.
You
Thank
can
you for
quickly go through
not
the
letting me go
slides.
on.
Yeah. Fernando, I initially sent you a message saying put it full screen, but I think you have missed it. It's okay.
Okay, so can you see it now?
Yes, we can. If you can
Yeah.
quickly go
Awesome.
through those again, that would be
Yeah,
useful.
of course. I'll do a brief review.
you.
So again, applications that we rely on based on NLP. Not everybody has access to those because there's a research imbalance between the different languages due to their popularity. Cross-lingual learning attempts to build a bridge between the different languages, right? And we usually work under a zero-shot setting in which you don't have labeled data for the target language. This has some difficulties, right? So the different languages have different syntactic properties and grammatical properties, right? Which make this task a lot harder than the monolingual version of it. There are cross-lingual resources that we take advantage of in order to overcome these difficulties, and these are parallel corpus, like the religious text, pseudo-parallel corpus obtained through machine translation, or pseudo-parallel resources like Wikipedia, and bilingual dictionaries, which are just pairings of words into different languages. And then we have word embeddings, right? The monolingual version, This was the example I was talking about, right? Where cat and kitten should be close to each other in the latent space, but should be closer to dog than they are to houses because they're at least animals instead of objects. And then you can do the sort of fun math with the words if you do king minus man plus woman equals queen, right? And then the multilingual version of that is basically the similar words in the multiple languages should lay close to each other in the latent space. But then you have the problem of these representations being fixed once you compute them, and that they should capture all of the multiple meanings for the words, right? So for instance, here, John was fired from his job. Fired means, he got terminated, right, from his job. And then here, the police fired a shot at the suspect. That actually means firing a gun at him, right? So, but even though these two words have very different meanings, the same representation would be used for those. So we landed where we were. So hopefully that was good enough. Okay, so in order to overcome this problem of the representations for words being fixed, contextualized representations were introduced. And at this moment in time, the best contextualized representations are obtained through language models. And language models, language models with transformer backbones. But language models do not have to have very complicated backbones like a transformer. You can create a language model with any method you like. I usually in one of my classes would create a language model with a Markov chain, right? Which is not very useful for representation learning, but it's useful for learning what a language model is. And a language model is just a probability distribution over word sequences. So it basically tells you the probability of a sequence of words in a language. And of course, the more common or the more frequent a sequence of words is, the higher the probability should be, right? So sequences of words that respect the grammar rules of a language should have higher probabilities than sequences of words that do not respect the grammar rules of a language, right? So when you learn a language model using a very complicated neural network or a very deep neural network like a transformer, right, which is based on the idea of self-attention, it turns out that if you learn a language model with a lot of text, right, the representations learned by the transformer are very useful to do some other downstream tasks, like event detection or other information extraction tasks. So at this point, this is the state-of-the-art way to obtain contextualized word representations, right? Which replaced word embeddings a few years back. And of course, there are multilingual versions of these language models. The idea is basically the same, but instead of training the model with text from a single language, you train them with text from multiple languages, right? So you have things like multilingual BERT or XLMR, which basically support over 100 languages each. But what multiple studies have found when they analyze the representations learned by these models is that the words from the different languages make very well-defined clusters. So for instance, in this image right here, right, you can see that in this example, they're using words from German, French, Russian, and Chinese. And you can see how the representations for each of the languages cluster very, very noticeably around each other, right? So even though you are able to obtain representation for words in multiple languages, it's very easy to tell them apart. It's very easy to say, oh, this comes from German, this comes from Chinese, right? Which is not always a good thing for cross-lingual learning, as I will show you later. So historically, there have been two approaches for people working in cross-lingual learning, which we call transfer paradigms. So how do you transfer knowledge from the source language to the target language? The first of those, or the first one people came up with, was called data transfer. So you basically have annotated data in the source language, right? So for instance, you have this sentence right here, John bought a new house, and you have the label for each of those words, right? So you have these labels O, T, O, O. And I'll talk about what these mean later. But for now, just know that these are words, labels for the word, right? So what you do in data transfer is you basically create a parallel or pseudo-parallel version of the original data. So here we translated this sentence into Spanish. So this is the same sentence, but in Spanish. And then you basically do some word by word alignment. So you say, okay, John corresponds to John, bot corresponds to compró, a corresponds to una, etc., etc., and house corresponds to casa, etc., right? And once you have that alignment, then you can just project the labels onto the aligned words. And now you have examples in the target language, in this case Spanish, that have labels, right? And then now you can train your model as you would train any monolingual a model, right? So basically you project the labels. That's data transfer. And it has its advantages, right? The main advantage is that the model that you train is able to learn the task specific information from the target language, which is the language you care about, right? It's able to learn from the word and label relationships, right? There's usually some, not some, like high correlation between the words and the labels, right? For instance, in event detection, the words we're looking for, the event triggers, are usually the verbs in the sentence, right? So there's high correlation between the words and the labels. So models using this transfer paradigm are able to take advantage of those, and they learn in the target language. The disadvantages should be clear in the sense that this alignment right here, when you align the words from the source language to the words in the target language, this is not always as clean as I'm showing it in this example, right? Because when you translate one sentence to a different language, the number of words, for instance, will most frequently not remain the same, right? So you have to make some adjustments there where one word in one language corresponds to a whole phrase in another, and that alignment gets complicated, right? So there are a lot of alignment techniques that people have come up with over the years, but even so, they're not perfect. So these alignment issues in the end cost or degrade the performance of your model down the line, right? And of course, there are also translation errors. If you're doing it in a let's say, professional way, if you're using like Google Translate, it's not perfect. Nothing's perfect at this point. Not even human translators, right? So that's the first transfer paradigm. And the second one is called direct transfer. And what you do in this one is, instead of projecting the labels, you only train the model using the source language data. So if you're working with Chinese, with English as the source and Spanish as the target, then you only train in English, but then you later evaluate in Spanish. And you're probably thinking, how do you even do that? Well, you try to train the model in a language invariant way. So by using language independent features or delexicalized features, and I'll give you an example of what those are in a little bit. But basically features that do not depend on the language, right? And by doing so, then you're able to apply your model directly to the target data, right? In this case, to the data in Spanish. Even though you just train in English, then you apply it to Spanish, and you should see, acceptable results. Not as good as the ones in English, but what we would consider acceptable. Now, the advantages of the direct transfer approach are that you do not need to do any translation or any alignment, right? Like we did on the previous approach. But the disadvantages are that you are not able to learn from the syntactic features or task-specific information in the target language, because all that you're learning about the task, you learn from the source language, right? You cannot leverage any lexical information. So both have their pros and cons, right? Now, that's about it regarding the cross-lingual part of my work. So hopefully that was enough context. The other part of my work is event detection. So I'll briefly go over the task of event detection. Event detection is a subtask of information extraction. It lays it around here. in this tree of subtasks. And what it attempts to do is it attempts to identify and classify the words that indicate the occurrence of an event. And we call those words event triggers, right? So for instance, in this sentence, John recently bought a house, right? The word bought, the verb bought, is the event trigger for an event of a transaction type, a transfer of ownership subtype, right? And as I said before, it's usually the verbs in the sentence that are the triggers for the events, right? But not always. So for instance, here in this example, the ceremony was led by the former Secretary of State. So in this case, former would be the event trigger of an event of the type personal and position, meaning that this person used to be the Secretary of State, but is no longer the Secretary of State, right? So that there's an event right there. And this is an adjective, not a verb, right? So it's a difficult task in that sense. And it's very reliant on contextual information because as you know, the meaning of the words depend entirely on their context, right? So when you mix these two settings into one, right? So you have cross-lingual learning and event detection, then you have a very complex task, right? So motivations for this is that creating data sets for event detection is very expensive and very it's very time consuming, especially, right? Because I've worked on the creation of several of these resources, and it's a lot of work just to come up with annotation guidelines that are consistent, because you always keep finding new cases, and then you want the annotations from all of your annotators to be consistent, and it's hard. So creating these resources is very expensive. So if you can avoid it, then if we could avoid it, then we would like to do it, right? So, however, because of the cross-lingual setting, then we have the additional difficulties that I talked to you about, like things like the triggers do not exist in the other language, right? Because there are words that do not exist in the other language. Or you have triggers that have multiple words, that have multiple meanings, and each of those meanings is a different word in the other language, right? So it's very complex. There are some data sets that have been traditionally used to evaluate models in this domain. So mostly, historically, the ACE05 data set, which has annotations in English, Arabic, and Chinese, and its ERE version that has annotations in English and Spanish. But more recently, there have been other data sets released, such as the Minion data set, which has annotation on more languages: English, Spanish, Portuguese, Polish, Turkish, Hindi, Japanese, and Korean, right? So this is a more varied, a more diverse set of languages that you can use to evaluate your cross-lingual model and make sure it's working all right. So in my work, my objective is to design strategies to improve event detection, but that are tailored specifically for the cross-lingual setting. And today I would like to talk about three of them, if I have the time. I'll try to go over them quickly. I think the most interesting part about this work is actually the motivation behind it, not so much the results. Those are just numbers. But yeah, so I'll show you three of the approaches I've used before. And I've used a direct transfer approach, a hybrid transfer approach, which basically combines the data transfer and the direct transfer paradigm. And then I also worked on on a few shot setting, which might be a solution for cross-lingual learning if we can create models that are able to learn from very few examples, because then obtaining very few labeled examples is very easy even for the most obscure of languages, right? So if we can do that, then we would probably solve the problem. In any way, so I'd like to begin with this one, right? So this was a paper that we published last year on NACL. The general approach, like I said, was a direct transfer approach to cross-lingual learning. And we are using a multilingual language model to obtain the representations for our works. The main idea, the main novelty of this work is that we refine an already existing idea known as adversarial language adaptation, which is very, very cool, very interesting idea, which I'll talk about in the next slide. So adversarial language adaptation was taken from another domain of research called adversarial domain adaptation. So in those words, they are trying to adapt two different domains. For instance, financial domain to educational domain, things like that. So, but when you work in cross-lingual learning, you can very easily see the correlation between treating languages as different domains, right? So you're basically trying to adapt the English domain to the Chinese domain or to the Spanish domain, right? So the idea is as follows. It's very intuitive, very easy to understand, but very powerful. A lot of people use it. So you have labeled data in the source language, and you have unlabeled data in the target language, because that's easy to obtain, right? Text with no labels, that's fine. You can get that. Then you have an encoder network, which whose purpose is to obtain representations for the words in both text, in the source and the target. And we have this, right? I talked about those. Those are the pre-trained multilingual language models that I talked about, like multilingual BERT or XLMR, right? But then you introduce these network or this small module called the language discriminator. So the purpose of the language discriminator is actually to tell the representations from one and the other language apart. So its job is to say, oh, this representation comes from the source language. So this is from English. And this representation comes from the target language. So this is from Spanish. And that's very easy to do at the beginning, right? Like I said here. So if you just use these models to obtain representations for words, it's very easy to tell them apart, or to tell the language they belong to, right? So the idea is, how can we make the encoder, right, create representations that are not indicative of the language they belong to, right? And so what you do is you present representations from both languages to the language discriminator, but then the outputs of the discriminator are used to train the encoder, right? So the encoder is trained in the reverse way of the language discriminator, and it starts learning to generate representations that are able to fool the discriminator. So basically representations that the discriminator looks at and goes, I don't know which language these two representations belong to, right? And those are language invariant representations, right? And then you use the representations learned by the encoder to do whatever downstream task you want to do. In this case, find event triggers, right? So that's the overall idea behind language adaptation. Like I said, it's a very simple idea, very intuitive, but very powerful. However, it does have its shortcomings, right? The main issue is that in standard adversarial language adaptation, all of the samples are given the same importance. And we thought that's probably not ideal, right? It's bound to be the case that some examples are more useful than others, right, for the discriminator. So we thought, what would we think would make sense, right? So we thought, what about we only present the discriminator with examples that are very informative for the task that we're trying to solve, which was event detection. So on one hand, we thought, if we present the discriminator with examples that are very different from one another, so examples in English and Spanish that are very different from one another, it's going to be very easy to tell them apart, right? So we don't want that. So we're only going to show it examples that are very similar to one another, right? So if the examples are very similar, then it's going to be very hard to tell them apart. And it's going to need to learn the very fine-grained differences between the two examples, right? And then our other measure of how informative a sample is whether it contains an event or not. So if an example contains an event, then it's bound to be more informative for this task. And if it doesn't have an event, it's probably not as informative. So in order to incorporate these two things into one framework, we are using optimal transport. And the idea behind optimal transport is as follows. It's a way to find the most optimal transformation between two discrete probability distributions. So if you visualize it in these images, you basically have this discrete distribution of points here, right? The orange ones and the blue ones, right? And you're trying to find which of the blue dots corresponds to which of the orange dots. And here it's very easy to see, right? Each of these correspond to each other. And the lines, how dark the lines between those points are is how much they belong to each other, how similar they are to each other, right? Or how aligned they are between the two. And if you visualize it using the moon's data set, right, you get something like this. So the idea is we want to find out these alignment scores between samples in the source language and the target language. And then we're only going to show the discriminator the examples with the highest alignment scores, right? And hopefully that improves the training, and then we obtain better cross-lingual performance because of that, right? This is basically what I said. So maybe from this slide, all I need to talk about is this. So we measure the distance between samples as the distance between their contextualized vector representations. So the representations obtained by the transformer, right? So we just measure the distance between those. That's how close to each other they are, right? And we obtain the probabilities of we obtain a probability distribution of how likely is each sample to contain an event. And for that, we just use a network that basically estimates the probabilities for each of the samples. And then we turn that into a distribution and we feed that into the optimal transport algorithm. And that's basically the main. I don't want to get too much into the details. I just want to give you a big overview of the intuition behind it. So this is how we model the task. So you have a sequence as an input, a sequence of words as the input to the model, right? And you also have a sequence of labels corresponding to those words, right? So John recently bought a house. This O means that this is not a trigger, this is not a trigger, this is the trigger, this is the type of the trigger, this is not a trigger, this is not a trigger, right? So you have words and their labels as their input. And then you have the encoder, which is just one of these pre-trained out-of-the-box language models, right? And the purpose is to receive each of the words, right? And then compute a representation for each of them, right? This is the architecture of our model. It's not that complicated. I know it looks like a lot, but it's really not. So you just have the input words. You have the encoder, the transformer encoder. This one will output the word level representation, right? But it also outputs a sentence level representation. If you know how BERT works, you've probably seen this before. There's a sentence level representation, and we use that sentence level representation to do the language discrimination. So we pass examples from the source language and the target language through the encoder, and then the representations are fed to the discriminator, and its job is to determine if it belongs to the source or the target language. And we also pass them to the event presence predictor, which basically predicts whether a sample contains an event or not, right? Then the representations for the words are fed to a conditional random field layer. Here we were just trying to take into account the relationship between the labels in a sentence, and these are used to output the labels for each of the words. So this is the ones that we use to do the classification, so to speak, and the main negative log likelihood law. So this is the structure of our model. But then the way we train the model is actually the one that does the trick. So we feed our representations to the optimal transport algorithm, right? And also we only use the samples that have the highest alignment scores from the optimal transport algorithm to compute the adversarial loss. And this is the whole trick. So we pass all of the representations from all of the samples go through the optimal transport algorithm. We find the alignment scores for samples between the source and target language. We only keep the ones with the highest scores, and only those are used to compute these adversarial loss, for which the formula is up here, right? And then we add that to our full loss, and that's basically the trick. This is just details on how we obtain each of the parts. I don't want to go too much into this. It's just Euclidean distance between the representations, softmax over the predictions from the event prediction module. This is how we compute the similarity scores for each of the samples. Again, if you want more details, I can go over them. I don't think they're needed. And these are our results. So at the time, we were able to beat the state-of-the-art model, but quite a bit, actually. So the state-of-the-art model was just, for this particular setting, cross-lingual event detection, it was just multilingual BERT with a conditional random field on top, and then they did the predictions, and these were the results at that point. And then our results, we changed the encoder from BERT to XLMR, which gave us a huge boost. But then our approach of only using the most aligned examples to do the adversarial training gave us an even larger boost, which at the time was the state of the art. So this was our model, and we tested on a lot of different language pairs using Chinese as the source, and then English as the target, or Arabic as the target, using Spanish as the source, and then English as the target, and so on and so forth. When we analyzed our model, we found some interesting things, right? So, for instance, the representations created by our model were orders of magnitude closer to each other than the baseline model. So as you can see here, they are like on the order of e to the -3 closer to each other. So this is e to the minus 10 to the power of -3, and this is 10 to the power of -6, right? So our representations were usually 3 orders of magnitude closer to each other than the ones of the baseline. This is just a visualization of which languages were closer to each other. So for instance, here, darker is closer, right? So English is very close to itself, but English is closer to Chinese than Arabic, and Chinese is closer to English than Arabic, and Arabic is closer to English than Chinese, right? But then analyzing the outputs, the actual outputs of our model, we were able to see that it actually handled polysemous triggers a lot better than the baseline. So just to remind you, polysemous triggers are triggers that have multiple meanings, and each of those meanings are different words in the other language. So for instance, these examples are in Spanish because that's my mother tongue, my mother language. So for instance, this word juicio in Spanish can mean both trial and judgment, like a judgment call, and trial like a court trial, right? And our model was able to handle these sort of example a lot better, almost a 30% improvement on these polysemous examples. And it could also handle conjugations better, like variations of conjugations. Like I said, different languages have different number of tenses, right? So being able to handle different conjugations of the same verb better is highly desired in cross-lingual learning. So these are just variations of the verb to buy in Spanish, and even synonyms, like these two are synonyms for the word murder, for instance. So in our next work, which was published this year at ACL, we actually tried a hybrid approach, which is, I think this is very interesting. So in this approach, we combine the direct transfer with the data transfer, right? So we both do annotation projection, but also train with language invariant features. So before our approach, all previous efforts in cross-lingual event detection had used the direct transfer approach, including our own, the one I showed you just before. So our main novelty for this work was doing a hybrid approach by leveraging a knowledge distillation framework where you have a teacher network and a student network. And the output from the teacher network is used to train the student network, right? And the problem with knowledge distillation frameworks or efforts is that usually the errors, so the teacher network is not going to be perfect, right? So the outputs for the teacher network are not going to be perfect. So it's bound to have some errors. And then you use those outputs to train the student model. So the student model learns to reproduce those errors. So they basically propagate the errors, right? Downstream. And that usually means that the performance of the student model is worse than the performance of the teacher model. So knowledge distillation originally, and maybe Nisansa knows more about this than I do, but I think that originally was designed to compact models. So to, from a larger model, train a smaller model with equivalent or almost equivalent performance. That was the objective of knowledge distillation. But in our approach, and in that sense, when you were doing that, it made sense that the student network performed worse than the teacher network. It was a smaller one, right? A more compact one. But in our approach, the way we're using knowledge distillation, the teacher and the student have the same size. They're basically twin networks. So because they're the same size, you actually expect the student model to outperform the teacher model. Okay, so how do you do that, right? If the labels that the teacher outputs are not perfect, well, our idea was we're gonna refine the examples that we use to train the student model. So we're not gonna use all of the examples that the teacher model outputs. We're not going to use all of them. We're just going to use a subset of them. We're going to carefully select which ones we use so that when we train the student model, it actually outperforms the teacher. So that's the gist of this work, the basic idea. So here's the overview of it. So we're going to train a teacher model using a direct transfer approach, like the one I showed you before. Actually, our architecture is very similar. So we're going to train this teacher model with a direct transfer approach. So we're only going to use the labeled data in the source language to train it with language invariant features. Then once the teacher model is trained, right, we're going to take some unlabeled data from the target language, and we're going to use it to obtain labels for it. So we're going to obtain labels for that target language data. But we're not going to work with hard labels. We're going to use soft labels. And what those means is we're going to work with the probability distribution that the model outputs, not the label you would select, say, using argmax. No, we work with the entire probability distribution. So then we're going to do a hierarchical sample selection. It's hierarchical because it has two steps to it. We select some samples, and then from those samples, we select another subset of samples. And then only the examples remaining after that hierarchical sample selection are going to be used to train the student model. And by doing so, our hope was to improve the training of the student model and that it would be able to outperform the teacher because the student model would benefit from training in the target language, right? And like I said previously, when you train on the target language itself, you are able to benefit from the lexical features, right? From the word label relationship in the target language. So you're not only learning from the source language, you're also learning from the target language. So that was our idea. And hopefully, I mean, fortunately, it actually paid up after trying for a few months. So the modeling is basically the same. You have some input, sequence of words as input with their corresponding labels. You have an encoder, which its purpose is the same. It takes the input tokens and outputs the hidden representations. And then we train that using the standard negative log likelihood. This is our architecture for the teacher model. It's very similar to the one I showed you before. It has a XLMR as the encoder. We have a language discriminator. We do that basically the same as before. It just has one key difference, and in that before, if you guys remember, when I showed you this architecture, I told you that we were using the sentence level representation to train the language discriminator. But in this other work, after reading other people's work, we tried, instead of doing that, now we're presenting it with the word level representation. So now we're showing it a bunch more examples. So we're showing the language discriminator, not with the sentence level representation, but the word level representation. So for each sentence, it's going to see a bunch of words instead of seeing a single representation. Same for the target language. So we're showing it a bunch of representations in the target language, right? So this is the way we train our teacher model. And then we train it as we did before. And once it's trained, like I said, we are gonna use its outputs, right, to train the student model. So now we're gonna take some unlabeled data from the target language, run it through the teacher, get its outputs, and then what we do is we do soft label training, like I said before, right? So what we're trying to do is get the student to match the probability distribution output from the teacher, right? So we do this because we found in several other works that by using these soft labels, the probability distributions, they have more information that the student could learn from, right? So we're not trying the student to output the same label. We're trying it, or we're aiming for it to output the same probability distribution. And how we do the sample selection. So we thought the teacher is bound to make some errors, right? But it's bound to make less errors in samples that are similar. So samples from the target language that are similar to other samples in the source language. So we're going to find which samples are similar to each other in the source and target language. And then we're only going to use the ones that are more similar to train the student model, right? Because if you use all of the samples to train the student model, then the errors in the labels that the teacher model generates will probably nullify all the potential benefits that you could obtain from the data transfer paradigm. So from training in the target language itself. So that's the basic idea. So we developed this hierarchical sample selection scheme in which first we do a global alignment level selection. For that, we use optimal transport like we did before. So we find out which samples in each of the languages is most aligned to the other language in a global sense. And then we have this cross-domain similarity local scaling selection, which basically does pairwise similarity. So which pair of samples in the source and the target language is most similar to each other? So the intuition here is we have like a global alignment step and a pairwise alignment step. And actually, without both of those steps, our model would not outperform the state of the art, which was our previous work. So this is optimal transport. I don't want to go into much into that. This is the formula for the cross-domain similarity local scaling. The main idea behind this measure, we didn't come up with this, by the way. This is somebody else's idea. So the main idea here is to take into account the neighborhood of a data point, because when you're trying to compute pairwise similarity or basically nearest neighbors, that's the problem of nearest neighbors. The data points that are in very crowded spaces, right, in very densely populated spaces, will be the nearest neighbor to many other data points, opposed to data points that are isolated, right? They probably won't be the nearest neighbor to any other data point. but they will have a nearest neighbor in one of those. So what this method is trying to do is to take into account that neighborhood to the other domain and to reduce the similarity score by taking those into account. So it's a better pairwise similarity measure than just doing like any distance or similarity computation. So these are our results. So here we're comparing with ourselves at this point. So this is our previous work. These were the results that we had before. And these were the results that we obtained. And on ACE05, the improvement was not a lot, especially in Chinese. But when you work on a data set like ACE05, which has been worked on so much, any consistent improvement is it's noteworthy. But then in order to better evaluate the worthiness of our approach, we tested on a different data set that hasn't been used a lot. The Minion data set that was just recently released last year, that wasn't released previously when we worked on our other work. And in this data set, our improvement over the previous reported performance was quite significant, right? So in some cases with improvements of over 25% in Japanese, for instance, right? So apparently this approach worked a lot better than the baseline. This is just the ablation study. So when we did the analysis, so here is the impact of how many samples you choose. So here it says performance impact of parameter alpha, and parameter alpha, what it did is it controlled the number of samples that passed through the first filter. So how many samples you kept after the first selection step. So here you can see if you keep all of the samples, if you keep 75% of the samples, 50% of the samples, and 25% of the samples. So as you can see, we obtained the best results by keeping half of the sample, right? And then this is what happens when you vary the beta parameter, which basically controls how many samples you kept after the second selection step. But remember that the input to the second selection step is the output of the first selection step. So if you kept half the samples here in the first selection step, then you just had half the samples here in the second selection step. And that's what we did. So by taking these results, we chose to keep half the samples after the first selection step. And then here is what happens if you keep, for instance, half of those samples, right? So that would be like a quarter of the original number of samples. So here, if we set beta to 75%, we obtain better results. And this is interesting because if you look at this graph, it would seem, right, like selecting more or if you keep less than half the samples, if you only keep 75%, or if you keep more of the samples, if you keep 75% of the samples, performance is degraded, right? All of these points are below these points, right? So it would seem like you can't do any more selection, but it turns out that you actually can, right? By setting beta to this. This is if we do no selection at all, right? We basically keep all of the samples selected in the previous step. But by doing some selection, right, 75%, we were actually able to push our performance a little bit. And this is what actually pushed us to a state of the art at that moment. So that's it for the second work. Nissan said, it's been 1 hour. Do you have a couple of minutes, or I can leave it at that?
Fernando, what's the situation?
If others are alright, we can proceed. I think.
Yeah, I don't have a problem. I'm just wondering if you guys have the time.
It's okay
Yeah?
by me.
Okay, so this is the last work I will discuss. So in here, this was published last year at the Multilingual Representation Learning Workshop at EMNLP. It got the Best Paper Award runner-up. So here we switched a little bit from the standard supervised learning training approach to a few-shot learning approach. And it was the first, this was the first work that basically combined few-shot learning with cross-lingual learning and event detection. And our main novelty is that we're actually proposing an entirely new few-shot learning method, and we were the first one to come up with this setting. So for those of you who are not familiarized with few-shot learning, supervised learning has its main limitation is that it requires a lot of data, right? So you need a lot of examples, and it does not generalize well to types that it hasn't seen before, right? So if you train with data with 8 different classes, and then when you test your model, you have a sample that does not belong to any of those 8 classes, it's not going to do very well, right? However, few-shot learning attempts to address this issue. So it's basically trying to come up with methods to train models using very few examples from each of the different classes that you have, so that they're able to generalize better. It's sort of how humans learn, right? Like, so when you show a baby a ball, it very quickly learns to abstract the characteristics of what constitutes a ball, right? Or a dog or a giraffe or a car, without having seen thousands of examples. With just 2 or 3 examples, we learn. So that's the basic idea behind few-shot learning. So the way they do that is by sometimes creating this. I'm a lot of I can't find the word. Restricted training setting, but artificially restricted, right? So you basically convert a data set that you could use to do supervised learning, and you convert it and you use it in a restricted way in order to do few-shot learning. And few-shot learning works as follows. So you have a support set and a query set, right? And both are composed by very few examples of very few classes. So you have, they're usually called n-way k-shot. So n-way is the number of classes that you have, and k-shot is the number of examples that you have per class. And n and k are usually very small. So they can be 2, 3, 5, 10, 20 is the most I've seen. And then you train your model on this setting, right? You train the model to extract features from the support set and use those features, or that ability to extract features, to classify the samples in the query set. And that's how you do the training. But then when you evaluate your model, so during testing, you use an entirely disjoint set of classes that were never seen during training. This is better visualized using an image. So this is how few-shot learning works. So during training, right, each of these is called an episode or a training task. So for instance, in this episode, in this task 1, this is K2 and 3. So you have 3 classes and 2 examples for each class. So here you have cats, sheep, and boars, right? And the query set, right, has samples from those classes. So you use this support set. The model is supposed to learn how to extract features from these examples and then be able to classify the samples in this query set because they belong to this class, right? And then in the next episode, you might get entirely different classes. So now you get dogs and sharks and lions, right? And then you extract features from these samples and then you use them to classify these samples in the query set, which belong to these classes, right? But then when you do testing, right? When you evaluate your model, you're not going to use cats or sheep or boars or dogs or sharks or lions because your model has already seen those during training. When you test, you need to use entirely different set of classes. So now you use dogs, dolphins, and chickens, and your model should be able to classify these samples, right? So that's the gist of few-shot learning. Very limited training setting. So again, this is how you model event detection as a few-shot task. You're going to have the support set and the query set. Each of these are going to be triples. They contain a sequence of words, a trigger candidate, and a label for the trigger candidate, which can be either the type of trigger it is, or it can be null if this word is not a trigger for an event. That's what makes it event detection. But on top of that, on top of the limitations of few-shot learning, we are working on cross-lingual learning, right? So under a zero-shot setting, but zero-shot in the context of cross-lingual, meaning that we train on the source language, but then we evaluate in the target language. So as you can see, it's a way more complicated task, because not only are we evaluating on a completely disjoint set of labels, we are also evaluating on an entirely different language, right? Without having seen data in that language at all. So it's a direct transfer approach here. So it's a double complication here, the few-shot and the cross-lingual. So our model is very simple in this regard. It's basically an encoder, again, a multilingual pre-trained language model, and a classifier, which is just a feed-forward neural network. The encoder takes the samples, the sequences and the trigger, the sequences of word and the trigger candidate, and it's supposed to output a representation for those. And then the classifier takes the representations for the entire support set, right? And one of the representations from the query set, and it outputs the label for that sample in the query set, right? So but using the entire support set, it's supposed to be able to classify each of the samples in the query set, right? So the problem that we saw with existing few-shot learning methods was that they they mainly considered the distances between individual pairs of samples. And our intuition was that if you took the global distance between the support and the query set into consideration, that should be able to help the model, right? Because let's say if the individual distance between two pairs of samples is small, but the global distance between the entire support and the query set is large, then the individual distances might not be as reliable, right? So we again leverage optimal transport, and the way we use it here is we're trying to align the samples in the query set and the support set. So this is an entirely novel few-shot learning method based off of the output of the optimal transport algorithm. So I haven't gone into details here too much on purpose, but I might need to for this part. So basically the output of the optimal transport algorithm is this pi star matrix. This is a matrix in which the individual cells is the alignment score between the samples in the two domains. So for instance, here, if this is the pi star matrix, right, the alignment matrix that the optimal transport computed, and here in this axis, we have all of the samples in the query set, and in this axis, we have all of the samples in the support set. Each of these individual cells is the alignment score between those two samples. So for instance, how aligned is the sample from the first class and the first example from the first class in the query set to the first example in the second class from the support set, right? That's what these numbers would represent, okay? So what we basically do is we take the output, right? This alignment matrix that the optimal transport algorithm computes, right? And then we use that to obtain classification scores. So what we do is very simple, right? So you have these matrix, like I explained it before, and then what we do is we just do class-based pooling. So we basically sum all of these alignment scores because they belong to the same class, right? These yellow ones. So how align this query example is to the first class. So we just add these 3, and we obtain this number, right? And then we add these 3. How aligned it is to all of the samples in the second class. So we add those all of those up, and we obtain this number, and so on, right? So from this matrix, we go to this matrix, and here you basically have the class-based alignment scores, and then we just do a softmax on these dimensions, right? And that turns this into a probability distribution, and that's how we do classification. But this is nobody had tried this for some reason, right? So this is an entirely new few-shot learning method based only on the output of optimal transfer. And then, in order to incorporate, the global distance between the support and query sets into our loss function, we are computing here the Wasserstein distance for the support and query sets, but we're also doing it in order, to tailor this work to the cross-lingual setting. We're also doing it for samples in the source and target language, right? So we're also computed the distance between samples in the source and target language, and we're incorporating those into our overall model loss here using a trade of parameters that we tune, right? So by doing so, we've basically created a model for few-shot learning and cross-lingual learning. And the way we did it, in order to do this training, like I said, you sort of like need to modify the data sets that you usually use to do supervised training. So in this case, the ACE05 and ACE05 ERE data. So what we did was we basically split the different event types into 2 disjoint sets so that we could use some of them for training and some of them for evaluation, so validation and testing. And this is how we split those types. So 4 types for training, 4 types for development and testing. And then we had to remove or discard some of the subtypes if they didn't have enough samples to do at least 5-shot setting, right? So any subtype that didn't have at least 5 examples in it, we just took out of the data set. So we ended up taking out some of the subtypes that existed in the data set. And this table basically tells you how many types there were for training. For instance, here English for training, we had 19 types after discarding all of the ones that didn't have at least 5 samples. And then when you create your episodes, you basically sample some of these types. So if you're doing 5 n equals 5, right? So 5 classes. So you sample 5 of these, and then sample 5 examples from those classes, and now you have your support set. And then you sample your query set, and then you do 1 episode of training. And then for the next episode of training, you resample another 5 out of these 19, and then create your support set, and so on and so forth. Hopefully that makes sense. These were the number of types for testing in Chinese and in Arabic. So just so you guys can see. And these are our results. So we were comparing against, the traditional few-shot learning methods, relation networks, matching networks, prototypical networks. And we managed to outperform them on this cross-lingual setting. This is our ablation experiment. And this is what happens if you combine our approach with the traditional approaches. And in all cases, we managed to increase their performance from the results you can see here. So if you incorporate our regularization terms into their approaches, they also improve their performance, which sort of validates our intuition. So that's basically it for what I want to talk to you about. So I've shown you 3 of the works that we've done recently. A direct transfer approach, basically optimize the adversarial language adaptation by only using some of the samples to train the discriminator. Then the hybrid transfer approach, which at this moment is the state of the art for cross-lingual event detection. Here we basically combine the two. We train the teacher in a direct transfer kind of way, and then we train the student in a data transfer kind of way, but we carefully select which samples were used to train the student. And then we also have these last few shot learning example, which might be a good direction to pursue, because if we are able to design methods that can effectively learn from very few examples, that pretty much might solve the problem of not having enough resources for some languages, right? And we think all of our methods are intuitive enough, or they're based on straightforward intuitions, right? I try to convey those, what our thought process was when coming up with these works. And we think that because of that, they are applicable to other tasks. So our methods are not married to event detection. They could be applied to name entity recognition or relation extraction, or other downstream tasks with maybe minor adjustments, right? So that's pretty much it. Thank you very much for being here. I hope you found it interesting. These are my emails in case you have any further questions after the talk. But I'm happy to take any questions right now.
Thank you, Larry. So it's time for questions. Let me start with the question on your second paper results. It was quite amusing to see that when you are using English as the pivot, Chinese was getting better results than Spanish. I think, yeah, here. Do you know why? Because Spanish is related to English and Chinese is not. But results seem to counteract that.
Yeah, I saw that as well. I actually don't know why. I thought it was interesting as well. It might be, I'm no linguistic, right? So it might be something about Chinese that I'm just not aware of. But I really don't know. I don't have an answer for that. That's interesting as well.
Yeah, because it seems like Arabic, again, unrelated, is also, it's less than Spanish, so that is not a problem. But Chinese, I think 75% was surprising. All right.
It also has to do, and this I know for sure, it has to do with the encoder.
Okay.
Nisansa. So if you use multilingual BERT, Arabic performs a lot better than it does with Robert XLMR. So it might have to do with the corpus that was used to train those encoders.
So there is a probability that this result is also dependent on the Chinese encoder being better than, let's say, the Spanish encoder.
Absolutely.
All right. All right. Others, please do ask questions.
Hi, hi, Dr. Fernando. Great presentation. I have a few questions, but I'll start off with one. So this work on event detection, how similar is it to like from what I noticed, like part of speech tagging of verbs?
So both are usually modeled as sequence labeling tasks, right? But one has to do more with the structure of the language and the other with the semantics of the language. So I would say part of speech is a lower level task, and Nisansa knows more about this than I do, but a lot of times part of speech tags are used as inputs in models doing things like event detection. The reason people don't do it yet in cross-lingual learning is because sometimes you don't have a part of speech tagger for the target language, for instance. But that's slowly being solved as more and more cross-lingual work is done. Now, there are many tools that do low-level, let's say, work for you that output like dependency trees and part of speech tags. And so more languages are getting these tools. So I think that's one of the research directions that people might follow, is start incorporating this, syntactic level or lower level information into cross-lingual models.
Understood. Great. And one more question. In your first paper, the results, you demonstrated the, using Chinese as source and English as target. And then, yes, this one. So, and then English as source and Chinese as target. Like, why isn't there like a big symmetry between those two, like the results, when you use Chinese as source and English as target, and like you can see like a massive drop. I mean, like 74, and here it's 45.
Mm-hmm. Yeah, I think that has to do again with, if I had to guess, I think that has to do with the way the encoder has been trained. So the
Right.
corpus used to train the encoder probably it had a lot more English text than Chinese text. So if you, I think this is the case, but I'm not entirely sure. But you could check it very easily. I think the results for monolingual event detection using Excel, I don't have them here because I was not interested in that, but I should probably have them. But I think the results. So for instance, if these cell or these cells were filled, I think these results would be higher than these results. That's what I'm trying to say.
Oh, okay. Yeah.
Right. So it would make sense if that's the case, which I think it is, that when you do this, these are also lower than this one. So I think that's where that discrepancy, that asymmetry comes from.
Oh, right. So in this kind of like models, like why didn't you like explore like translation models? Like, because they already have they might have an embedding in the shared space, closely aligned cross-lingually, right? Like, general translation models. Like, is that angle people can go with for like?
Yeah, absolutely. Yeah, I think that's a very worthwhile direction to. So you're saying maybe a pre-trained translation model is already able to obtain representations that are very aligned between
Yes.
languages, right?
Yeah,
Yeah,
because
that's certainly something you could pursue. I would say it's very likely that those will have good results, but on the same sense, it would depend a lot, because I don't know. No, I would be saying things that I'm not sure of. So yeah, I think it's a worthwhile direction.
thank you so much for your time.
Thank you for the question.
Others in the audience? All right, then, given that we are also about half an hour. Oh, there is all right. Everyone, please have a look at the feedback form as well, and give it, fill it. Fernando, I hope that you have taken note of the people who have dropped out in the middle, so that we can send it to them as well. All right. I take this opportunity to thank Louis. Thank you very much for taking this opportunity to talk to our students and our audience. Obviously, I like the the topic because I worked in the area as well, as you may have guessed. And I hope that others got an idea of how this cross-lingual work works, and especially and on the other side of the event side, which I'm not obviously working on. But hope we had some audience members who are interested in the event processing side as well. I think in the Sri Lankan context, there is Siddhi with WSO2, which is big on handling events. So maybe if any of you are from that project team and so on and so forth, maybe these papers are things that you can introduce to your other members and see whether these can be implemented in an implementation such as Siddhi. All right. Thank you very much again. And we shall see you on a next research talk. Thank you, Fernando, again.
Thank you, Nisansa. I was very glad to be here. Bye.
Bye.
Thank you. Bye.